3 or 4 or whatever, okay? And they will bind to different things. In this particular case, we have 2 labeling cells here. And what we find is this red protein, labeled red, because of how it fluoresces. We'll bind the tips here of this, while in this other cell, it binds the axon. Okay? So these are the tips of dendrites, the tip of the axon. But most typically, this protein called tau binds axons, and so that's one way of identifying where an axon is. There are others, microtubule-associated proteins. There's 2A and 2B. These 2 are very typical of dendrites, so if you put an antibody against this thing, let's see what it is. It's just a protein that these cells have a lot of, that like to bind to microtubules. You put an antibody against that, these cells, what you'll see is mostly shining light on the dendrites of the cells. So these are the kind of techniques that you'll see used, and we'll probably show you maybe more pictures probably along the duration of this course, that we can use to identify where is a receptor. Let's say you have a receptor against whatever, substance P or something, or this substance involved in pain perception, or acetylcholine, which is a neurotransmitter released by neurons. And so you make a good antibody against it, put it on the preparation of the tissue of your interest, and start going where the tissue is producing that hormone. So it's a very, very nice, very specific, and beautiful way of showing where these things are. All right, that, well, here's another example, but this is kind of a good slide to segue into the next thing I want to talk about. Here you have actin, and remember actin is part of these microfilaments that I mentioned last time. In muscle, it's very tightly associated with myosin, and is involved in this crawling of these 2 filaments past each other. Actin is involved in the same kind of process of crawling over other molecules. Very often, well, other types of myosin also in the nervous system, not just in the muscle. So, and here you can, I mentioned this, I showed this last time, but again, here you see it associated with what? What do we call these structures? Spines. Very good. Synaptic spines. No question. Synaptic spines, pre or post-synaptic? Pre. Can you both? It's post-synaptic. Okay. So the spines are these little protrusions that contain the receptors, the postsynaptic end of the synapse. What do we call? They're not always there, but what do we call the presynaptic structures? Presynaptic structures that maybe look a little bit like a spine. Boutons. Boutons. They look a little bit like that. They're not as spiny. Okay, that's why they call these spines, because they have this kind of spiny look, different lengths and different shapes. The boutons are maybe a little more like a little knob. And those are found on the presynaptic side. So what is this? This is an astrocyte. An astrocyte is one of a family of cells that I mentioned before, I think, that are found in the central nervous system, central and peripheral nervous system, which we call glia. Okay? So here you see the glia. So glia derives from the word for glue. In the late 1800s, was identified as a cell in nervous tissue that didn't look exactly like neurons. They had very typical shapes, shown in this diagram here. The astrocytes is a cell that looks like a star, right? That's what it looks like. And this one is an oligodendrocyte. What does oligo stand for? Mean? Multiple. A few. Few. Very good. Oligo is few. And dendro? Finger-like? Finger, exactly. And inside the cell. So it's a cell that has few dendrites or few extensions. That's what this says. So it's good to know Greek. Let's look at that too. Microglia, what does that mean? Small, tiny. Okay, so there is a difference between them. These look a little bit like that, but they have much fewer of these, and we'll see there are some other very important differences. Microglia are very tiny and have some of these processes, and astrocytes have a lot of them. So initially glia were thought to be, because they're local and they're always found between neurons, and because people just had the idea that neurons were special and glia were not, so they were relegated to the category of just glue, just holding things together and not doing anything else that's of any use. Now we know that it's not true at all, that glia are very important, they do a lot of things, but they don't transmit signals at a distance. They don't have the processes to do that, they don't have axons. Although they have these finger-like things, which we don't call dendrites. So in glia, although this is obviously kind of says, contradicts me right there, by contradicting that, but people really don't call dendrites the processes of glia. Okay, so they're just processes or extensions. But they have a cell body, they have these things, but they don't have synapses. They don't produce synaptic vesicles. Remember, we talked about that a lot last time. Those little blobs in the presynaptic terminals. Glia don't do that. Glia don't do a lot of other things, but otherwise they look very much like neurons. And we'll talk a little bit more about that later. But they do one very important thing. Well, they do